Our next presentation then is given by Mr. David Carlin, a Science Director from CFAS, and this is on behalf of the Ocean Governance SIG, considering regulatory issues for deep sea mining. So hopefully that question will come to the fore.
Thank you very much, and good morning, everybody. It's a great pleasure to have been invited to come and talk to you about deep sea mining this morning. The last public talk I gave was at a workshop at Lancaster House, and I thought that venue couldn't really be beaten, but I think Trinity House certainly is up there with Lancaster House. I've been involved with the Institute for around a decade now, so I was really pleased to be asked by the chair and co-chair of the Ocean Governance Special Interest Group to come and give this quick talk, canter through what is a pretty large and complex topic of deep sea mining. My background is very much in environmental regulation, particularly in the UK context and increasingly internationally. However, I am going to endeavour in my talk to give you a sort of, hopefully an all-encompassing overview of the topic of deep sea mining. The detail, I'm afraid, will be rather sketchy because it is such a broad topic, but hopefully you'll get a flavour for the area. And indeed, I'll talk a little bit about the need, the geology, locations for the deep sea minerals, some of the technological issues, and then a little bit more about the governance and how we understand the environmental impacts as we move on. So, deep sea mining, it's a hugely controversial, emotive, interesting and complex topic. Extracting rare earth minerals from the deep ocean, an environment we know very, very little about, creates very, very strong and polarised opinions in all sorts of different directions, as you can imagine. But why? Why is there a need for deep sea minerals? As we move towards a low carbon and a digital future, we need to access an increasing supply of rare earth minerals, silver, gold, copper, manganese, cobalt, zinc, the list goes on. Terrestrial resources across the world are increasingly becoming exhausted, and poorer quality, the environmental impacts of extracting these poorer quality resources increase. So there is an opportunity to look to our oceans to provide those, really important minerals for this future economy. Microchips, solar panels, offshore wind, electric cars, they all require, access to these really important rare earth minerals. So as a society, there's an opportunity for us to make a choice as to how we can provide the resources to support these wants and needs into the future. So the resources, there are three principal types of deep ocean mineral resources. We have, on the left, we have hydrothermal vents. On the bottom left, right as you look at the left as you look at the screen, we have crusts. And then the large picture shows a field of manganese nodules. For those who haven't seen them, they're a sort of cricket ball sized lump of multi-metallic rock which sits on the seabed and can be effectively harvested, brought up to the surface, processed, and all sorts of minerals and rare earth metals extracted from those nodules. The reason the picture of nodules is bigger than the other two pictures is very deliberate. Manganese nodules are reasonably well understood. They're reasonably well understood in terms of their distribution around the planet. They're reasonably well understood in terms of how they can be extracted and removed from the deep ocean, much more so than the other two types of geological deposit, and therefore are likely to be the first type of deep sea minerals which are extracted from the high seas. So where are these deposits? These deposits are all over the global ocean. The image to the left is the Clarion-Clipperton fracture zone in the middle of the Pacific Ocean. This is principally an area where most activity in terms of deep sea minerals in the high seas is taking place at the moment. It's an area that's been defined and is in the process of being regulated by the International Seabed Authority, which I'll come on to later on in the talk. And this is also the area where where polymetallic nodules are principally found and are being sought to be exploited from the high seas. There are substantial sulfide deposits as well as nodules in the Indian Ocean, and I know they're being considered at the moment for extraction by a range of different nation states. There are polymetallic sulfides which can be found in the mid-Atlantic ridge, and cobalt-rich ferromanganese crusts in the Pacific Ocean as well. These principal geographical areas relate to high seas. However, there are a number of deposits which are found in individual nation states' economic areas, and those particular deposits are also being looked at under a different set of processes, very much driven by individual nation states who have access to their own mineral reserves. So how do we extract deep sea minerals? I should emphasise that at the moment, any extraction for deep sea minerals, with the exception of some work which is about to start in territorial waters off Papua New Guinea, all of the extraction to date has been for scientific research purposes. There is no commercial exploitation of deep sea minerals quite yet, and I will come on to explain a little bit more about that later. But in essence, irrespective of the type of mineral that is being exploited, it has to be harvested from the seabed. If it's manganese nodules, large-scale vehicles are deployed onto the seabed, which effectively can harvest the materials, a bit like a combined harvester may harvest a field of wheat. This material is then pumped up a riser pipe. We're talking about water depths of in excess of 4,000 metres, so you can imagine the technology to pump hard minerals from at least 4,000 metres in the deep ocean is a huge challenge and an area of technological development which is ongoing. Minerals are pumped up to the surface, they're processed aboard a ship, and then they're either shipped to land or processed at sea potentially to extract the actual mineral content from the manganese nodules and the other sources that have been harvested. To harvest hydrothermal vents, that's a little bit different in the sense that extinct hydrothermal vents will need to be effectively cut off and risen to the surface. Crust deposits need to be pulverised on the seabed, and there's different types of technology that's being developed to look at how that might be possible in the future. But as I say, the focus, certainly globally at the moment, is very much on manganese nodules and the extraction of those materials. Just some examples, images from the web of some of the technology that's been developed to extract materials. So we can see at the top of the image there some rather brutal looking technology which is developed and built up in the northeast of the UK by Soil Machine Dynamics. Those pieces of kit are being tested, I understand, down in the South Pacific at the moment, particularly around the Papua New Guinea claim I mentioned earlier. The image to the bottom left, this is a trial system called Patania 2, which has been developed by Deme Dredging Company in the Netherlands. This is the second prototype of a deep sea nodule harvester that will be tested later this year and next year in the Clarion-Clipperton zone in the Pacific Ocean. Patania 1 was maybe about a third of the size of Patania 2, didn't have any of the harvesting equipment attached to it, and was used really to prove that a tracked vehicle can be driven at 4,000 metres depth successfully, and that was a successful trial. Patania 2 has now been developed to really see if the harvesting technology can work as well. But in terms of the technology, there are lots of other questions which colleagues within the Institute will have views on and can certainly make contributions. You know, propulsion, how do we propel harvesting devices in an environmentally sensitive way? I deliberately won't use the word sustainable because obviously we're talking about a finite resource which is being extracted. How can fleets of harvesting vehicles be propelled autonomously? Are there opportunities for artificial intelligence to be used in the operation and therefore the management of deep sea minerals? How do we power them? Currently the Britannia system used umbilical cords which power the vehicles, but you know, there are opportunities for other power sources that need to be thought about. How do we deploy them? How many do we deploy? How do we service them? And how do we create efficiency in the operation of the extraction of deep sea minerals? So lots of technological questions which still need to be answered in terms of the feasibility, if you like, and the practicalities of extracting minerals from such a harsh environment. The next critical thing really is developing our understanding of the impacts of the extraction of deep sea minerals. We've got lots of knowledge gaps, and Ralph's talk identified earlier the amount of data that we collect within the marine environment, or could collect, provided the governance arrangements were in place. The deep ocean is a huge challenge, and there's a lot of work still to be done to understand things like ecosystem connectivity, the impact of the gene pool at deep ocean being changed. What are the impacts of introduction of artificial light into deep water environments? What are the impacts of the introduction of noise to those sorts of environments as well? What are the recovery timescales post-extraction, and what are the environmental impacts of that? Lots of questions still need to be answered. The reality, though, is that we won't be able to answer those questions unless, and one school of thought is that mining takes place, because of the sheer cost of collecting that data and monitoring those sorts of environments. So it's a bit of a catch-22 situation. Do we mine to understand more, or do we not mine and try and understand more through other means before mining takes place? We need to understand how we develop an assessment of serious harm. Serious harm is something that's enshrined in the United Nations Convention of Law of the Sea, which has established the regulatory framework for deep sea mining in the high seas. Of course, different nation states have different interpretations of serious harm based upon their own particular economic or environmental concerns and needs. So there's a challenge there as to how we can define that better. How can we implement a precautionary approach so we can start to understand the environmental effects of deep sea mining in a more collective and collegiate way? And how do we, as I mentioned earlier, how do we gather data to create baseline conditions, recognising the expense is vast of doing that data collection exercise? The photograph there, it was actually my Lancaster House talk, and what we've done is to engage with the UK academic community, who've done an awful lot of research into the impacts of deep sea mining, and we've engaged with a number of relevant institutes, colleagues from the Natural History Museum, the National Oceanographic Centre, many members who are actually members of the institute here, and a number of the technical working groups and special interest groups have already had their opportunity to contribute to how the UK particularly develops its position around deep sea mining. And this will continue. This was the start of a conversation, and I'd encourage colleagues here and online to get involved in that conversation as the opportunities arise. The next thing we're going to be doing is looking at how we can develop standards and guidelines for exploitation. As I mentioned, there is no exploitation of deep sea minerals in the high seas at the moment. The intention is that the International Seabed Authority, who regulate this activity, will start to lay regulations in 2020. And to support regulations, there's going to be a need for guidelines and threshold values and standards that can be adopted to govern and manage those impacts. And there's an opportunity to shape what they look like. So looking at understanding the impacts, we looked at other sectors and how do other sectors regulate some of those activities. You can see from the table there are a whole range of different impacts, from loss of substrate to the big impacts of plumes, both at the ocean bed, but also mid-water as minerals are pumped to the surface through the riser pipe, changes in light levels, potential increase in toxicity in water columns. All of these things are regulated currently in the UK and internationally through different regimes. So what we're actively looking to do across government is look at how we've got best practice already in place, how that can be applied to that deep water environment, and ensure that we can get into a position to make some really pragmatic decisions about how we can regulate the exploitation of deep sea minerals into the future. So the legal context for deep sea mining, I've mentioned the International Seabed Authority a couple of times already. The ISA was established under the United Nations Convention of Law of the Sea, UNCLOS, to manage all of the deep sea mineral resources in that high sea environment, in that high sea area, i.e. those areas beyond national jurisdiction. The United Nations established the ISA to ensure that they had a role to govern the common heritage of mankind, recognising that these minerals are there for the global population, not just those nation states and companies who can afford the technology to get out into the high seas and exploit them. The two main organs of the International Seabed Authority are the Assembly and also the Council. The Council meets twice a year in February and then towards June and July. And I've had the privileged position to sit on the UK delegation to the ISA Council for a couple of years now. And it's a really interesting fora for discussion and seeing how that sort of interface between politics, diplomacy, science and technology really starts to come together. All parties to UNCLOS have the opportunity to sit in the Assembly and also be elected to Council, and therefore make decisions on that sort of global scale about how deep sea minerals can be managed. The ISA also has its own legal and technical commission. This is a group of nationally appointed experts covering everything from ecology to law of the sea. There are geologists, deep sea fisheries biologists, a whole sort of smorgasbord of different expertise sits on the legal and technical commission and informs the council on some of the matters that it really needs to consider to move forward with pragmatic exploitation of deep sea minerals. So, as I've mentioned a few times, at the moment there are only a number of exploration licenses that have been issued by the International Seabed Authority. We haven't formally moved into exploitation. The ISA has adopted exploration regulations in relation to all of the three mineral types I talked about at the start of this particular talk, and has so far issued 29 licenses for exploration of deep sea minerals to 20 different countries. Nation states, members of the ISA, are able to nominate a sort of sponsored company, if you like, who can then potentially go and undertake exploration and therefore exploitation into the future. Different nation states choose how that works in practice. Some countries have a national company that's established, a government company, to explore and exploit. Some countries like the UK, for instance, very much adopt a sort of free market approach, and there was a selection process to identify a commercial company who could potentially work on the two UK sponsored zones in the Clarion-Clipperton zone. And that company is UK Seabed Resources, which is a subsidiary of Lockheed Martin, the defence contractor. So there is a timeline for the development of regulations for the exploitation of deep sea mining. The regulations are in their third iteration, and council members have all been encouraged to contribute, and they have actively contributed to the drafting of those regulations. it is the intention of the ISA to lay those regulations by 2020. I think there's an opportunity for the Institute to make a contribution to those regulations as well. So sort of the key issues that are coming out from some of those draft regulations, I've talked about a number of these already, but how can the ISA effectively take account of the environment? The UK recognises as part of its position that we have to be absolutely clear that environmental impacts are the highest issue here for us. If we go into a pristine, unknown environment, environmental standards have to be very, very strong to ensure that we make as minimal impact as possible on those particular resources. We've got to adopt the precautionary principle and really actively use the precautionary principle to enable us to understand more about the environment in which we're potentially going to be exploiting minerals. Regional environmental management plans are important as well. So how can we address cumulative impacts by monitoring and managing not just individual individual concessions that have been issued by the ISA, but collectively within particular regions that I mentioned towards the start of the talk. So a whole range of different activities that bring together regulation, science, industry, technology that need to be looked at to ensure that that ambitious timescale of 2020 can actively be met. So what happens next? I've talked a bit about these already, but we've got an opportunity to test existing technology at depth. I talked about Petania 2. I showed some of the images of the soil dynamics systems, but there's a lot more work to be done there. We've got to develop the riser pipe technology. There's a whole opportunity from an engineering and a technology point of view to understand how we can pump minerals from such depths in a safe and sustainable way. How do we process minerals? Do we do it at sea? Do we do it on land? What are the economic costs? What are the societal costs? What are the needs? Do we need to ship this material around the world? Do it where energy costs are low? Where are the minerals needed? A whole range of different questions to be answered there. I've talked a lot about the science. We've got a lot more work to do to understand the environmental impacts of deep sea mining and apply those in a pragmatic way that links in with the regulation of this activity. And going back very much to Ralph's talk around technology and data collection, there's a whole opportunity to develop a range of different technological monitoring systems to understand the environmental impacts and the physical and the societal impacts of deep sea mining as we potentially move from exploration to exploitation. So very much a sector in its infancy, lots more to do, but the pace is quick and there's a huge opportunity for the Institute and others to actively engage with that. Very happy to take questions now, but you can contact me through these channels. I'm not a particularly prolific Twitterer, but there's my Twitter link. So I do occasionally tweet on deep sea mining, particularly when I'm at the ISA. So if you're interested, you do have a look and you'll find out some of the people that I follow as well. Thank you very much.
David, thank you very much indeed. I particularly love the breakdown into the engineering, science and technology. This is a subject this just has so much going for it and so much for the Institute to engage in, which is fantastic. I'm going to pass over to Bev for questions. We do have many, so we apologise if we don't all get picked up, but we will do our best.
So setting the standards, we've had over 20 questions, Dave, for you. What we will do is we will take all the questions from today and ask our special interest groups to answer them. So if they're not answered in this forum, the special interest groups will provide a answer. Sorry if I've dropped the special interest groups in it. We have our first question, most popular, is are there any governments that are actively regulating for deep sea mining in their EEZs or territorial waters, and what's being done in enforcement of this?
So the first sort of non-high seas area, as I mentioned, is Papua New Guinea. So the Papua New Guinean government have been through an extensive environmental impact assessment process. The activity hasn't started yet, but I understand it is due to start in due course. And within the regulations and within the consents that have been given, there are a number of monitoring requirements that have been established through that environmental impact assessment process. Going back to high seas, as I say, the regulations the ISA intend to lay next year, and there's a workshop coming up in Pretoria in South Africa in May, which the UK is sort of helping to shape, and hosted by colleagues in South Africa, which is intended to start to identify some of those sort of monitoring and enforcement requirements that are going to be needed sort of in the high seas exploitation of deep sea minerals.
And then I think these two are probably two we can bunch together. Can deep sea mining be a force for good? And if so, how close are we to viable ocean floor mining? Ecologically viable.
I think the force for good. I remain as a civil servant. I have to remain neutral on that, but I refer you back to my first or second slide. We have a choice as society. Do we want a low carbon future? Do we want to embrace digital technology? If so, we need rare earth minerals. They have to come from somewhere. They could come from the deep ocean. They could come from terrestrial sources, as they do at the moment. So I think there's very much a societal need there. And as I mentioned in the talk, the technology to exploit is being actively developed. So I think viable extraction of deep sea minerals is, particularly manganese nodules, is not far away.
Okay. Okay, in interest of time, we will move on. But David, thank you again.